Good morning. My name is Pritahir. I'm from Warren High School in Downey, California.
I'm Nathan On, and I'm from Palos Verdes Peninsula High School in Palos Verdes, California.
My name is Bryant Liu. I'm from Footridge Preparatory School in California, and today we'll be talking about optogenetics and their applications to color blindness. All right, the abstract. Before we dive deeper into this, can I ask, who knows what optogenetics is? Raise your hand. Oh, that's quite a few of you. Well, for the people that don't know, optogenetics is basically a technique where scientists shine blue light onto the species animal's brain, in which they could trigger natural behaviors such as aggression or motor functions like moving the arm. Now today we'll be applying optogenetics to potentially curing color blindness, in which we will be shining light onto the occipital lobe of the brain, and which will trigger the cones in the eyes to receive more light.
So let me give you guys some social context and a little bit of background about how our eyes perceive color. So, or first, hold on, let me start with the question. What percentage of males and females do you think have color blindness? Just out of curiosity. Or what percentage males and then what percentage females?
I have a guess. I would say 30% of males and maybe like 5 to 10% of females.
Nope. No? Anybody else?
Straight denial, man.
60 male, 45 female.
Nope.
Not even close.
One more. That's really close, but no. Actually, it's 8% males and less than 1% for females. The reason why is because males have X and Y chromosomes and females have X and X chromosomes. So the chromosome that carries this trait is on the X. So because females have two X's, that it gets transferred over to males. It has a higher chance of getting transferred over to males than females. Okay, so color blindness is when people, okay, so there's different. Okay, much better.
Yeah. Yeah.
This week was that there's two different receptors for color. People have rods and cones that perceive light and color. So rods allow us to perceive black and white. So I guess, they allow us to perceive black and white. And then when cones are what allow us to perceive color. That's the part that we want to try to fix, because cones allow different amounts of light into the eye to help perceive color. So when people's eyes, I guess, don't let in enough light in a sense, they get different variations, such as that. So that's why there's different types of color deficiency. So there's like tritanopia. Yeah, you guys get the point. So essentially, that's what causes that. And then this affects a lot of people around the world, like 8% of males around the world. That's a huge number. So if we were able to cure this, we would essentially be allowing numerous people to we open their eyes to a whole new world of color. Like,
Literally.
Imagine somebody wants to become an electrical engineer, but then they can't because they can't tell the difference between a red and green wire. Stuff like that. So that's part of the reason why we wanted to research this a bit more.
So the main question of this is to find out what part of the brain controls the cones, which is primarily responsible for color vision in the eye. And these receptors also allow insight of the mapping of the brain, which is a huge concept of the Brain Initiative. And their main mission or goal is to completely understand the brain.
All right, precedents. So there are numerous amount of scientists that are also researching using optogenetics, such as here at CNSI, Dr. Katsushi Arisaka, in which he used, like the example before, he used optogenetics to trigger aggression in mice. I wanted to show a GIF, is that how you pronounce it? I don't know. And basically, what he did was he put a stick with with mice in it. And when the blue light is not turned on, the mice do not attack the stick. However, when the blue light was turned on, the mouse attacked the stick, in which proves that optogenetics did trigger some sort of aggressive behavior in the mouse. All right, and here's our project proposal. So our team will use optogenetics to try to reduce or remove color blindness from the person affected, and we will do so by first applying anesthesia to a live human patient, because we can't really do this with mice because they can't give us a response on whether or not they see color or not. They'd probably be like, squeak, and when they don't see color, and a higher pitcher squeak when they do see the colors that they don't see. So I think the only way we could do this is probably with humans, in which we actually develop a language that can actually help us communicate with each other. So first we'll be applying anesthesia or not, depending on the patient and what they prefer. And we will be probing, we'll be using optical microscopes, a mounted optical microscope, to see some places in the brain, and we will probe some areas part of the occipital lobe, which is the lobe responsible for vision. And so basically, we'll just keep probing and probing until they say, like, whoa, color. And basically, when they do say that they see color, we will use fluorescence microscopy, in which we will inject some fluorophore or GFP into that area of the brain, and that will react to the neurons inside the occipital lobe, and we will see. What do my notes say? And we will shine blue light in that area to see where the GFP is, and we could apply it to. If we find the right neuron in which they reacted to, we could potentially change the future of neuroscience and add more to the mapping of the brain, which is, sorry to mention, this topic's related to the Brain Initiative, in which they're responsible for, our mission is to map the brain.
So people with normal color vision are called trichromats, and people with the faulty color vision they're known as anomalous trichromats. And the main confusion is that once people experience color blindness, they don't really know what type, because there are many broad types of color blindness. But there are three main types. There is the proteinomia, which is a reduced sensitivity to specific red light. And there is deuter anomaly, which is the sensitivity to green light, and it's also the most common type of color blindness. And then also there is the trite anomaly, which is a reduced sensitivity to blue light, and is the extremely rare case and is the most uncommon case of color blindness. So here is more charts on the specifics of the three types of the color blindness, on where people can perceive different types of color for the normal color vision. So in this photo, the top left picture is someone with the normal color vision, and the top right is someone who has tritonophobia, which is a reduced sensitivity to the blue light, which is also the most uncommon case. The bottom left is the normal color vision, and the bottom right is the deuter anomaly, which is the reduced sensitivity to the green light, but also the most common case of color blindness.
So discussion. So to summarize, essentially, or based on the experiment that we saw on like the first day of class, we want to see if we're able to trigger, so the blue light was able in the video we saw, in which the mouse has blue light shining on its mind, it triggers a sense of aggression in it. So we want to see if we're able to trigger something that'll cause the cones in the retina to, in a sense, like perceive more light to help people perceive color. And however, as one of the issues is that we may accidentally like randomly trigger the wrong thing, as in like the mouse. We don't want to trigger aggression in people, but that may be an issue we may run into while testing it. But however, once we conduct those tests, obviously we hope to release it to, or we would hope to bring it to hospitals and so forth to help cure color blindness.
These are our contributions, and these are our references. Thank you very much.
Any questions? Oh wait, no. After the questions. After the questions. Questions? Oh wait, actually, so I want to explain that picture. We actually were in one of the labs, and we wanted to see the fish that they were working on, and I managed to take a picture of it, a video of it actually, and that one came out really cool. So we thought, why not show you guys? But yeah.
And this is thanks to Dr. Bentolila for letting us see the fish in the microscope.
Yeah. So any questions?
First of all,
Yeah.
okay. First of all, you guys are so hilarious when you are presenting. It's perfect. Like, it really helps. It really helps bring some character to what you guys are presenting.
Thank you.
So,
Thank you.
what I wanted to ask, how is using this optogenetics going to affect the cones that are related to color vision? Like, is there some way that that using this light is going to, like, are the cones damaged or something? Is like, what's the reason behind color blindness, and how is using this going to help?
Okay, so essentially so the eye is able to see because it lets in light and so forth, right? So what happens in the cones is that if it doesn't receive enough light, because like it's kind of like you're shining light through a hole, and then you have receptors on the back that will decode it in a sense. That's like a rundown version. But with the issue with the cones is that they're not letting in enough light, or in some instances they're letting in too much light. So we want to see if we're able to, in a sense, like or you know how cameras have apertures, how you can open it and close it? We want to see if it's something like that, because if it is, then that could potentially solve our problem. Yeah. Any more questions?
So aren't the rods and cones on the retina in the eye, not in the occipital lobe? So why would you use a microscope for an occipital lobe?
Okay, so basically, you use a microscope for the occipital lobe to locate the neurons in which you're probing, which could possibly be connected to the cones. And so when you probe the occipital lobe and it triggers the cones, we would use the microscope to locate that specific neuron, and we would inject the GFP to locate that neuron, and we would provide a cure for color blindness for that specific person.
And then the occipital lobe is responsible for vision for the brain.
Does that answer your question? Okay.
We have time for one last question, if there is one.
So
Yes?
I get the gist of what you're trying to do, but I'm trying to understand where the microscope comes into play, right? I mean, at the end of the day, it sounds to me like you need to genetically modify the neurons in the occipital lobe of the brain, and then you're going to try to figure out where to pulse them with blue light to manipulate the cones in the retina, basically, right? So what do you need to visualize to do that? I mean, you're going to try to mount a microscope onto the head of some human or some animal, right? What are you looking for, other than the fact that you have basically genetically modified neurons in that region that you can stimulate with light?
Oh, sorry, I didn't clarify. Is the doctor or the person using the probes on the occipital lobe that'll be wearing the microscopes, so they could locate that specific neuron?
So you think that there's some specific neuron or set of neurons in that region of the brain that you would want to stimulate?
Yeah,
Yes.
And you need to figure out what it is, where it is, so that you can...
essentially, yeah.
Yeah, that's where the GFP comes into play.